Okay, so for the benefit of everyone, if you think about where we've come from so far with our bonding, we've done ionic bonding. So we've actually talked about ionic lattices. And then we've also looked at metallic lattices, which is something up here in the classroom. And our third type of bonding that we've been working on now for a week or so is covalent bonding. The section on covalent bonding, you recall, is all about molecules. So wherever we are talking about molecules in our bonding, we have to now begin to expand our knowledge a little bit. And this stuff that I'm going to go through today is something that is conceptual. So you've all got kits in front of you of various molecules that we've now built, okay? But I figure, or I'm hoping, that if you can see the molecule in 3 dimensions, that hopefully the stuff we're going to go through now will help reinforce your understanding, okay? I know we've got ChemSketch and some beautiful resources, but it's nothing like seeing the real molecule like in your hands and working out why is it that shape, okay? So this is what we're about to launch into now. So the term that we use is called Vespa Theory, okay? Not Vespa motorbike, nothing to do with Vespa motorbike, but it's valence shell electron pair repulsion. And this is the words that make up Vespa Theory. And it's frightening when you think of all these words, okay, and what they actually relate to. We're looking at essentially the shape of a molecule. And the shape will determine how a molecule is going to react. I might have talked about the shape of hemoglobin last week when we talked about how enzymes work, okay? And for those of you doing biology, you might have heard of what's called a lock and key mechanism. And so a lot of the stuff that happens inside of our body is dependent on the shape of molecules. If we know the shape of a molecule, then it has a certain functionality. And we said hemoglobin is designed to fit right in the middle a molecule of oxygen, okay? It's actually shape dependent. The other thing that is very important in terms of shape, and you might not be aware of it, right, is solubility. Now we haven't done a lot of stuff on solubility yet, but you might not know why is it, for example, that if you have an oil spill, why do they use things like detergents to get rid of oil spills? Or why do you use kerosene to dissolve an oil spill? Why don't I just get water? Because water is essentially a different shaped molecule, okay, than an oil. Because of different shapes, they don't interact with one another. So when we look at shapes of molecules, the next step on is we're going to look at how the molecules interact. And that means we need to understand shape, because shape affects something that you're not even aware of yet, but shape affects what we call polarity of a molecule. Polar. What do you think about when we say polar? What do we think? Magnetism. So like a north and a south. Similar with a structure, okay? So it's got like a north and a south. However, in terms of polarity here, we talk about electron rich with a delta negative or electron deficit with a delta positive. So it's either got lots of electrons or not many. Okay, shape. Valence means we're always dealing with the bonding or the add electrons. That's straightforward. Shell, we all know what electron shell is. Electron. So we're now talking about the electrons that are in the bonds. Okay? But we're also talking about not just electrons that are in the bonds, but here I've put down pair. So the word pair comes up. So when we were looking at the structure for water, we actually drew the structure for water in this shape here because we said that it's actually got non-bonding pairs of electrons. So when I talk about pairs of electrons from now on, I'm talking about bonding pairs and also non-bonding pairs, because they are all essentially going to have a negative charge. That area there is going to have a negative charge, that's got a negative charge, and that's all got negative charges. So all I want you to understand is that when we're talking about shapes of molecules, whether they're bonding or non-bonding electrons, they will affect the shape. Everyone cool with that? Okay. The next thing is, knowing that, repulsion, the last word repulsion, like charges repel. Just like Ethan said before, so a north and a north, if it was a magnet, they're going to repel. The hard thing with Vespa theory, stop playing with your models, okay? The hard thing with Vespa theory, alright, is how and why do electrons repel? Hopefully you can work that out, alright? So what we're going to do is, we're going to look at some shapes of molecules, and basically we're going to do it simply first, and then we'll just build up the complexity. This little round dot here is supposed to be one atom, and that there is another atom. Okay, that's all it is. Now, if I have a molecule that looks like that, and you've actually built one, here it is, okay, an oxygen molecule. Okay? The only thing that affects the shape of the oxygen molecule would ultimately be the electrons in the middle. There's only one group of electrons. How many pairs are we talking about here? How many pairs? Two pairs. There's two bonding sets, okay? But they are right between the two atoms. So hopefully you can work out, there's only one shape I could ever get for an oxygen molecule. Anyone guess what the shape would be? Just linear, good. Straight is another word, alright? But the shape for this is actually a linear molecule. Okay, so here's one sort of shape that we can look at. Maybe I started with a more complicated one, but here it is again. Okay, this is, again, if we look at the structure, you can draw it. Here it is again. And perhaps I need to be a bit more specific. We'll put a double bond there. That's more like it. A double bond. Okay. This has now got a single bond. Okay. How many pairs of electrons are involved in the bonding? One pair. Okay. One pair only. What do you think the shape of that molecule is going to be? Linear. Okay. So up here, if I were to draw the structural formula for oxygen, there it is. Doesn't matter which way around I draw this one. That's the structural formula for hydrochloric acid. So you've got one, okay. This is also a linear structure, okay, same shape. So we've got two molecules. Based on their structure, all right, they are linear because they can't do anything else. We've only got two atoms, and all the electrons are stuck between the middle of the two atoms. All right, they have to be in a line. Now, let's go slightly more complex. We've now got this one, okay? This one looks like this. And I'll put a double bond there, and I'll put a double bond there, okay? To show you the structure. This is the structure for carbon dioxide that we touched on last week. So if I draw the structure for carbon dioxide, we'll just simply do it like that, okay? That's a carbon dioxide molecule. But, okay, and the question is, why have I drawn the carbon dioxide like that? And last week, some of you could have done it like that, and you would have got the valence, so your carbon ticked off, that's it. Carbon's got 4 bonds, oxygen's got 2, okay? So why didn't we draw it like this? Ethan?
Because the electrons repel.
Which electrons are repelling? The valence electrons, or the bonding electrons in this case, are repelling. Okay, so the question is, is there any electrons around carbon that I haven't accounted for?
There's 4 on the top.
There's 4,
Yeah.
But where are they all being used though, of course?
Bonding.
They're all in bonding, aren't they? So if there's one here, one here, one here, and one here, there isn't any electrons left. Okay, so this has actually only got 2 groups, 4 pairs, but 2 groups. It's got a set here, and it's got a set there. It's only got 2. This is simple. It's only got 1. That's only got 1. 2 pairs, but 1 group of electrons. So if I've only got 2 to worry about, only 2 groups of electrons, hopefully you can see, if we've got our 2 groups of electrons, and if that's all we're worried about, okay, it's very technical. This negative area is going to repel that negative area, so they have to ultimately be a linear structure. Does that make sense? They have to repel to linear to be as far apart from one another as possible. Okay? And that's the case for carbon dioxide. This one here is a bit of a different one. So if these were to do this, if the oxygens were to bend down, these electrons are getting closer to these electrons, so they're going to repel back again. Alright? These molecules do vibrate, by the way, so in space, this carbon dioxide will vibrate, but essentially the molecule is going to be linear. Okay, everybody happy with linear structures? Alright, now, that is all our linear structures. So we've got HCl, here it is, carbon dioxide, or oxygen, okay? Any molecule that is a simple, either two groups or one, has to be linear, okay? It can't be anything else. Now, let's move on. The next one is a little bit more complex, okay? So over here, all right, when we talk about pairs of electrons, I should probably split that down. We'll say pairs here, and I should say just big groups. Pairs, there are two. Groups, one. Here, there's only one pair, there's only one group. In oxygen, there's actually four pairs, there's four bonds, but there's two groups, okay, in the carbon dioxide structure, all right? So we've actually broken it down simply to the number of groups of electrons that are around the atom, and that will impact the shape. Okay, questions with that one? Everyone happy? Okay, we'll just stop there.